Okay, so everyone, and so let's just recap what we were doing last lecture. So we were talking about doing measurements, quantum measurements in other bases, and so just to refresh your memories, so when you have a measurement, then you might start, this is the qubit example, you might start in a state like this, and then what we said is that when you perform a measurement, it will change the state. So you can't do a measurement in quantum mechanics without actually changing the state. And if you get the outcome 0, then this will happen with probability of this coefficient squared, modulo squared, and then 1 coefficient absolute value of theta squared. And basically, in either case, basically the state will then change. And we talked about measurement operators and how we can apply these operators. And then these will also give these same probabilities. And also, you'll get this new state depending on which outcome. So this is a random process. And, mathematically, it looks like you can just apply whatever measurement operator you want, right? You're in control of like what operator that you apply to the state, right? So if you wanted to say, oh, I want to work out this case here, you just apply this one, right? But in the real world, physically, actually, this is totally unpredictable. And so you can't actually control which one of these ones are going to happen. And so even though mathematically you can kind of apply the operator that you want, you can't actually control it when you're actually doing it physically, right? Like in the lab. So, and we also did, I think last lecture, this idea of basis rotation. So we could look at different coordinate systems, and they could equally describe any state. And so we started off by saying that we can describe a state in terms of, say, these two states, 0 and 1. But actually, there's a lot of different other bases that you could potentially choose. And so here's another one, S0, S1. Typically, we'll choose orthogonal bases, so S0 and S1 are orthogonal states, and I think I told you a rule last lecture about how to make orthogonal states for qubits. Basically, the rule is that you kind of swap these, and then you take a complex conjugate and put a minus sign, and then that makes another orthogonal state. For qubits, the rule is simple of how you make an orthogonal state. In general, it's sort of more complicated. So I wouldn't really even know a formula that does it. You sort of have to do it through some procedure, maybe like these procedures like Gram-Schmidt orthogonalization, things like this. So it can be done, but it's not like a simple formula. Okay, and then so we can have a state, and we might write it in terms of this other basis, S0, S1. And this is not like 0, 1. And basically the content of this slide set is to say that actually we can also perform a measurement, not just in the 0, 1 basis, but we can also do a measurement in this other basis, S0, S1. And of course this S0, S1 is just arbitrary. So this S0, S1 could be any pair of orthogonal states. And so basically how it kind of works when you perform this measurement in this other basis is that you start with a state and say you've written it in this basis already, right? And then in that case, there's some measurement machine that does the measurement. It will collapse to either S0 or S1. So, one of these two states, red states. And then it will happen with the probabilities, the modulus squared of coefficients here. So, basically, it looks basically the same thing. It's just that the measurement is now, not in the 0, 1 basis, but in the S0, S1 basis. Okay, so where we got up to? Did we do this slide? Maybe not. Yeah. Yeah. I can't remember if we did it, but if we can't remember if we did it, then maybe we should go through it. So there's a simple example of this. Yeah, maybe we did do it. There's a simple example of this. I talked about measuring in the plus or minus basis. So instead of 0, 1, we're going to measure in plus and minus, and they're defined like this. So the plus state is like the state it's like a equal superposition state of 0 and 1. So it's like kind of like 50-50 in 0 and 1. But then there's a plus sign between them. Right? Minus state is the same thing, but it's got a minus state between them. And so what we, I think, did was that, say you had this state here, alpha beta. Now we can rewrite this according to a basis change into the plus minus basis. And the way that you do that was that you kind of rewrite these relations in terms of 0, 1. So you've got to invert these relations. And remember, we did something, I think, we did it together where we could invert these ones by like adding these two equations together, for example, and then that would give you 0 on the right-hand side because the ones cancel. And then to get the relationship with 1, you subtract the equation. So eventually you have the inverse relations look like this. They look kind of like they are originally. And so using those relations, we can rewrite the original state in terms of this. And once you've rewritten the state in this basis, then the measurement rule is pretty easy. You just look at whatever the coefficient is in front of it, and then just that's the modulus squared of that gives you the probability. So the modulus squared of this one is that, and basically the measurement outcomes are just plus and then the minus state. So depending on what type of measurement you make, as in what basis you measure in, then the probabilities will change, right? And I think a point that I made in the last lecture was that remember that when you have this state like psi of alpha 0 beta 1. So if we change the sign here, right, to minus b, or have an I here even, if you measure in this 0, 1 basis, there's no difference to the probabilities. It doesn't matter that it's minus or I or something. The probability of this one's always beta mod squared. The probability of this one is always alpha mod squared. But then with this minus sign, say, you can see that, well, okay, so it depends on it. So say it's plus or minus, then this will drastically change these things, right? Depending on whether this is a plus or a minus. The signs and the fact that these are complex numbers make a big difference. If you're measuring in a basis like this, but if you're in the 0, 1 basis, actually doesn't change it. So, by doing different measurements, you kind of see different parts of the wave function. Actually, doing the measurement only reveals like part of the information actually, right? So, measuring the 0-1 basis here gives you some information about like the probabilities. Like actually, basically what it does is, if you do the polar decomposition of these numbers, so maybe R prime. So in the 0-1 basis, because it gives the probabilities are like alpha squared for this one, and the probability of this one is beta squared. And then this one would be R squared, right? This one would be R dash squared. So in the 0-1 basis, it just gives you information of these R's, right? But it doesn't tell you anything about these, the phases, like these angles, the polar angles, or the complex phases. So it kind of only gives you, part of the information when you do a measurement in a particular basis. So if you look in a different basis, then it will give you information about say, these angles. There'll be some dependence on theta and phi if you look in, say, this plus or minus basis. Okay, so, yeah. I think what we will now do is to basically just repeat this calculation here, but then do it in the measurement operator formalism. Okay, so basically we should get all the same results, but just a slightly different way of getting the same answer. Okay, so the framework is still entirely the same. So remember when we write these measurement operators, they look something like this in our case. So this M0, this would be like the two different outcomes of the measurement. So in the example here, it would be like, say, plus. Right? M0 would be plus here. M1 would be minus. Those are the two different states. But otherwise, still the same. So probability is just a formula like I gave you before. So you calculate this quantity, and the state that you get after the measurement is this quantity, m psi, and then you normalize it with this factor. Okay, so let's give that a try. So, so let me just go through that. So what we're starting with is this state. It's a bit dark. All right, so we're starting with this state, alpha 0, beta 1. Okay, and so in the measurement operator method, what we're going to have are like two measurement operators. Stick to the same kind of notation. Now, of course, we can do something like, rewrite this thing in terms of the plus and minus basis. But I want to show you a slightly different way, which also works. And this is maybe a little bit easier. So, first step, as usual, is to calculate this quantity m times psi, because when we want to calculate like the probability, we're going to calculate the norm of that thing m times psi, and over here we're going to normalize that. So let's just plug that in. So this is m, and this is psi. Okay. And then we can just expand this bracket here. So you're going to get plus, and you get alpha times plus, inner product with 0, and you're going to get beta plus inner product with 1. Okay. Okay, and then now I've got to work out what. So these are numbers here, right? Inner product always gives a number of some sort. But what is the number? How do we work it out? So I've got it down there, but let me write it out. So to work out what this thing is, again, we can just substitute the definitions of plus. And plus state we defined. That's the definition of the plus state. But taken the bra version of that, so all the vectors are pointing that way. And there's no complex numbers here, so I didn't have to take any complex, well, okay, it is the complex one here. Okay, and then here's 0, and then we can just expand it out. So this is 0, 0, 1, 0, and this is 1, this is 0. So we use this orthogonal rule a lot. So basically this is equal to 1 over root 2. Yep. Similarly, if you do overlap inner product of plus and 1, well, you can just see here, 3. The only term that will survive is this one, not this one, right? Yeah. So this will also be 1 over root 2. So now we've worked out what those numbers are. And so this is 1 over root 2, this is 1 over root 2. So this is that's just whatever that number is. And it's that. So notice that this state here, actually it's always going to be plus, right? So, it doesn't really matter what's happened here. Like this plus is just always there because, the only action, anything that happens in the calculation is over here where we've got this bra and then this ket, which is the state. And all this stuff always gives a number. And then you just got this ket here, which will just carry on through here. So, well, this makes sense because when you do a measurement, and basically we're looking at the outcome where you get plus, right? So, because we're looking at the outcome where you get plus, the state is always plus, right? Basically, but up to some number. And this number gives you information of the probability. So the probability of getting this outcome, so as usual, is that. That's the general formula. And it's basically just the norm of this thing, right? The norm of that. So we just have to take the complex conjugate transpose of that. And then just that itself. Okay. And then this is just the numbers, so they can all go out front. This is that. Now you got plus inner product with itself. And generally we always normalize these vectors. So I can just about immediately say this is 1. But if you like, we can just check that that's true. And so if you look at the definition of this plus state, take the inner product of it with itself, Yeah.
Is the denominator?
Oh, yeah, you're right. Thank you. And this will be half. So this term will be 1. This term will be 0. This term will be 0. This term will be 1. So this will be 1 plus 1. That's 1. So it's a normalized state. So just to verify that you get the right normalization. And so, yeah, so this is 1, and we get alpha plus beta over 2. So that's the same answer as what we got using a bit of a different way. The way that we did it here was we started here, rewrote the state in terms of this plus minus basis, and then just took the modulus squared of that, and then we get the same answer. Okay, which is easier? I don't know. It sort of depends on the situation. Maybe for this one, it's similar. I mean, I was pretty explicit in writing this. If you get used to these types of calculations, then you might be able to squeeze this down into maybe 2 lines or something. But yeah, okay, so that's the probability. And then the actual state that you get at the end is the what I call it, psi measured state. So that's m0 times psi. Divided by square root p0. And so this is alpha plus beta over root 2 divided by the square root of this thing, so it's modulus of alpha plus beta square root 2. And the state itself is plus here. These cancel, and well, up to some phase, whatever the phase is. Yeah, okay, so I didn't really say it, but yeah, up to some phase, so I don't know what the phase is, just depends upon these coefficients, because it's like basically alpha plus beta divided by modulus of alpha plus beta. Up to some phase, it's equal to plus. Okay. Yeah.
Is that e to the I x or I alpha?
Yeah. So that's the phase. I mean, maybe I should have introduced a new symbol here. So what I mean by that is just alpha plus beta over alpha plus beta modulus, and this is basically some kind of phase. Because in general, alpha and beta are complex numbers, and so, you know, that divided by the modulus always gives just some phase factor, with like the r here is 1, right? So this is some phase factor, but in quantum mechanics that phase is not important, because it's basically a global phase, and this global phase is kind of unobservable. Okay, all right, so that's kind of like 2 ways of calculating the measurements. So the first way is simply, step 1 is to rewrite the state in terms of the new basis that you're measuring in, and then just read off the coefficients, right, and modulus square, to get probabilities. Second way is using these measurement operators. Construct the measurement operator, take the overlap in a product like here, and then that will give you some coefficient, and then coefficient squared is the probability. Okay, so, right, okay, so that's the basic, the basic message, for this slide set. But what we want to do now is just to just look at a kind of an application of this, which is distinguishing quantum states. And this is sort of not really a problem that comes up classically, because basically classically you can always do it perfectly, but quantum mechanically because of this kind of strange way that measurements work in quantum mechanics, there's different kind of property or different dynamic. So that's what we're going to talk about. So let's look at this kind of scenario, and we're going to look at different scenarios. So this is the first one that we're going to look at is the classical case. And the type of scenario that we generally have is something like this. We've got like a measurement device, and this measurement device is something where you can feed some particles in. This is where the particles go. It has some readout, so that's like maybe 0 or 1 if it's a qubit. So this zero here, that's basically the readout, right? So the machine tells you it's either 0 or 1. And finally, there's a knob at the top where you can change the basis. Right? It's kind of a theoretician's version of the experiment. Right? And you can change this basis so that it's like 0, 1 basis, or plus minus basis, or any other basis that you want. Okay. So this box is something that I'm going to use a lot in the coming lectures too. So what we're going to do is we're going to look at different scenarios of like feeding in different types of states. Okay. And so the first simplest case that I'm going to consider is that we're going to feed in a bunch of different classical kind of states. And what I mean by classical is that those states are just like 0 and 1. Okay? So these are supposed to be like counters, like various games, I don't know, checkers or something. One side's red, one side's yellow. So just like that, or coin. Basically you have two states and you're going to feed them in. Now, obviously, in this case, in the task, what we're trying to achieve is that we're trying to, we're receiving these things. So imagine like you are on the receiving end, you've got one of these devices here, somebody is sending you a stream of these things, and your task is kind of to figure out what the state of these counters are. So, you've got this stream of particles, a bit like, maybe you're trying to communicate or something, right? So somebody's sending you a message in zeros and ones, and you want to receive that message. And so you want to know, okay, is it 0, is it 1, is it 0, is it 1? Okay, so in this case, obviously, you can do it. There's a perfectly good way to figure out if it's 0 or 1. If you know that all the states are going to be 0 and 1, then you just have to set your measurement machine, to the 0, 1 setting, and with 100% probability, you will get like the right state, right? Because if the state that is coming in is 0, and your measurement operator, say, is 0, right? Then m0 psi, better in there. M0 of psi is 0, 0, and let's say 0. Okay, that's 1, that's 0. Probability of this thing is, well, probability is, that, which is 0, 0, 1. So 100% probability you will get 0, the 0 outcome with the input state 0 if your measurement operator is 0. Now what about the other outcome? In 1, okay, in 1, well, M1 on psi gives 1, 0. Okay, so that's 0. So this is 0 vector, as in the vector with length 0. Probability of that is 0. So basically, with 100% probability, you will get the outcome 0, and with 0%, you'll get the outcome 1. So that means you can perfectly tell the difference between the zeros and the ones. I mean, as you should, because that's what we do every day, and that's how the internet works. Maybe in practice it's 99.9 with a lot of nines, but it's pretty much close to 100%. Okay, so that's easy. There's no surprises there. Okay, so now let's look at something that looks a little bit more quantum mechanical. So we've got the same kind of setup. Okay, but this case we are actually going to send not zeros and ones, but pluses and minuses. Plus states, minus states. Okay, well, this is definitely, looks a bit more quantum. There's a superposition involved in the states, right? Now, the difference is that these states have a different phase, right? So this is 0 plus 1. This is 0 minus 1. Okay? But actually, even in this case, you can still tell the difference between the two states perfectly. And the reason is because, well, if your measurement, if you got your measurement settings, you're allowed to turn this knob and change this to the plus minus setting, right? Okay. In that case, then basically what we can do is just pretty much like what I just explained here, except that this one will be plus. This is input state is say plus. The measurement operator is plus plus. What will happen here will be like plus product of plus and plus. It's actually 1, just like we did that here. Output will be just plus. Probability of getting that will be plus of product of plus is 1. And the other case, plus and minus states are orthogonal. Just check that they are. So if you've got plus state, other way. So these are orthogonal states because here and here this will give 1. That's 0. That's 0. This is minus 1. Plus and minus are orthogonal states. And the probability of getting minus outcome, if the state is actually plus, will be 0 because this will involve this orthogonal product, plus and minus. So actually, even though this one looks a bit more quantum, It's actually not really so different in the end. So it tells you that, well, actually, even if the underlying states are quantum, so long that the states are like this, and your measurement settings are on the right thing, then you will be able to tell the difference. Now, of course, if you suddenly, say your measurement box was on the plus minus setting, but then you suddenly change the particles to 0 and 1, right? Then it's going to mess you up a lot. So to show you what would happen in that case. So, say your measurement operator was plus minus, but then your input state was just 0, then what's going to happen is that M0 applied to the state will give this plus state overlap in a product of plus and 0. This one we worked out before, it's 1 over root 2. Okay. And the probability of this outcome will be the norm of this thing. And then so you will get probability half the this 0 outcome. Right? So basically, and this will be random, and for the other measurement outcome minus, you can do a similar calculation. M psi, this is going to give minus state over root 2. Probability of this outcome will be half. Okay, so this is what I'm doing here is a situation where the states that are going into the box are like this is my measurement box. But my setting here is still on the plus minus basis setting. Right. So if my box is kind of on the wrong setting, then I can no longer distinguish between the states because it's the wrong setting for the box. Classically, you don't really have to think about this because there is no other setting. There is nothing else but 0 and 1, right? It's just only two choices. Information is 0 and 1, and your readout is 0 and 1, and there's no other choice. But quantum mechanically, you do have another choice, right? And so if kind of your box is on the wrong setting, then you will not be able to distinguish the states. Okay. Okay, fine. But basically, still in this plus minus case, you still can. You can tell the difference. So long that you got your box on the right setting. But now let's look at a case where there's just no setting available to tell the difference between these states. And so let's look at this case like this. So suppose, we go back to putting our measurement setting on 0, 1. That's the basis that we're measuring in. Okay, but now let's say that our stream of particles here can be any kind of random state where maybe sometimes it's 1, sometimes it's minus, sometimes it's 0, sometimes it's plus. Let's say there's like 4 choices that it could possibly be. Okay, in this case, actually there's no way to actually reliably read out that information. So with the box on this setting, for these ones, you would get the right answer, if you like, every time, right? So because it's on the right setting, here's a 1 basis. So 100% of the time you would get 1 reading for this one state, and you would get 0 reading for this one. But then for these ones, you would just get 50-50, 0 and 1, just randomly. And it doesn't tell you if it's plus or minus, it just gives you random 50-50 noise. Same with this one. So for the plus state, randomly it will get 50-50 noise. And you might think, well, I don't know, maybe you're on the wrong setting, right? Maybe we should choose a different basis setting here. And maybe we could tell the difference between these states. And so, well, clearly it can't be the plus minus basis because you're actually going to end up with the same situation as here. So if you put this in the plus minus basis setting, then you will be able to tell the difference between these ones. But then now you can't tell the difference between the zeros and ones. And so you've still lost half of the particles. Okay, so maybe there's even some other clever basis that you could choose, right? A way that you can visualize these states, right, is so say the 0 state and the 1 state here. The plus states are kind of 45 degrees along here, right? Now maybe you could somehow choose some other angle between these plus and minus 0 and 1 states. Right? Basically, it turns out you can't. There's basically no angle that you can choose such that you can reliably tell the difference between these 4 different states. Basically, you will always kind of have some failure rate, right, in telling the difference. So if you chose, say, this blue one, which is like, say, halfway between here, now I think you would more probably, you would, with some probability, which is like probably bigger than a half, correctly guess that this state is 1 or plus, because basically this one is kind of quite close to both of these ones. But because it's not an orthogonal state to both of these states, it doesn't do it with 100% reliability. And likewise here too. Okay, so yeah, so well, I do have this exercise here, but so choosing halfway between the states would correspond to actually choosing an angle. So this one is like 90 degrees, this one is 45, so for example this one will be 67.5 degrees. Okay. And so what I've got as the exercise is work out the probabilities of getting S0 and S1, show that it's not possible to distinguish between the states. Well, maybe I can just sketch it because I think you guys mostly get the point now. So suppose the state that we're trying to measure is say 1. This one here, here. And suppose we're going to use like this S0, S1 basis with say this angle here. Then okay, so suppose we choose S0. Well, okay, so let's do S1 actually. I think that's a little bit closer to the yeah. S1 would be sine theta cosine this, and then so the probability of getting this one. So firstly, the measurement operator for this outcome would be S1. We apply this to the state input state. So we've got S1 state. Now we've got to work out what this thing here is. Actually, it's pretty easy to read off because the inner product. Okay, maybe you guys could tell me. So what is this inner product going to be? S1 inner product with 1. Yeah, minus cosine. So it's just like this term here. So this is going to be minus cos theta S1. And then, so the probability of this outcome is just this one as usual. Norm of this factor here. This is going to be cos squared theta S1. This is normalized, and you can quickly see that this is normalized because inner product of this one is going to have a sine squared plus cosine squared. That's 1. So the probability of this is going to be cosine of theta. Now, cosine squared of theta. Cosine squared of theta is only 1 if theta is 0 or 180. So choosing this angle 67.5 will not do you any good. You're always going to have some failure probability where this is not going to give you 100% readout of the state. So this is actually not just a sort of a theoretical example. It's very close to how famous quantum cryptographic protocol works. It's called BB84. Everybody heard of BB84? In the quantum cryptography world, this is basically the most famous quantum cryptographic protocols. Like maybe one of the earliest, or maybe the earliest, invented by these two guys. Charlie Bennett, Jill Prasad, 1984. So it's just named after their paper, their initials, and the year that this paper was published. And basically they showed that using this kind of scheme, they can transmit information securely, and that that basically it should be fundamentally kind of secure. And if you know anything about cryptography, so modern cryptography works on the principle that basically you encode your information. So whenever you transmit any information on the internet when it's encrypted, basically it's done by kind of coding the words, but these encodings actually work because essentially that it's tied to some kind of mathematical problem which is very difficult to solve, right? It's very difficult to solve. It's not impossible to solve. It's if you had a powerful enough computer, then you could actually solve it and in principle break these codes, but the assumption is that nobody has such a powerful computer, and so basically for all intents and purposes you cannot break these codes because nobody's got a powerful enough computer. But I mean that's based on some assumption. Who knows that if somebody does have like a very powerful computer somewhere? I mean you're sort of assuming that everybody's computing capabilities are roughly the same, and there's not some genius somewhere in some country in the back inventing his own computer, which is so much more powerful than any computer that anybody the and the rest of the world is built, right? So, I mean, you know, we're pretty confident that, you know, the computing capabilities of things are relatively, everybody has access to the same types of computers. So, you know, it is pretty secure, but basically this one it's based on a different principle. It's more based on the laws of physics rather than any kind of limitations of computing capabilities. So this one, you know, quantum mechanics basically says that you just cannot kind of tell the difference between all these ones. So basically there's no measurement setting that you can have such as to correctly distinguish between these things. And basically distinguishing between it is basically the task that you have when you're sending information, right, or receiving information. If you can't receive the information properly in a way such as to obtain the data that's encoded here, then your information is kind of failed. And so this BB84 relies kind of on this aspect that if you look at the information this way, encode the information this way, then you can't really decrypt it. And that's based on laws of quantum mechanics rather than any limitations of computing. I didn't really explain what the actual protocol is, but that's basically the underlying kind of principle that's important in this BB84. So maybe, you know, if we have time, we might talk about that later on. But I think for now no, that's the last slide at all. Okay. So so any questions regarding measurements and bases? Okay, so then I think the final topic for this slide set is quantum demography. This is a little bit similar to the setup that we were talking about, but it generalizes it a little bit more, I suppose. So the setup that we're thinking this time, it's not so much that we're trying to receive some information this time, but this time basically we're trying to figure out what a given quantum state is. And this time what's going to happen is that Alice, who's the sender of the information, is sending, in this case, qubit, in some quantum state. And basically the task of Bob is to figure out what the state is. He doesn't know what the state is, and he's got to figure out what it is. Right? And that basically, and figuring out what the state is basically means figuring out what are these parameters, theta and phi, because that's the coefficients of the wave function, and the wave function determines the properties of the system, and so figuring out these parameters basically tells you what is that state. Okay, and now I said early on today that if Alice only sends kind of one of these states, then actually it's impossible for Bob to really work out what this state is, because well, actually, sorry, I didn't really say it earlier on, but what I did say earlier on is that using like a 0 and 1 basis measurement, you can tell what maybe the this parameter theta would be, but you can't tell what phi is, right? Because when you do a 0 and 1 measurement, then the probabilities come out with the absolute value squared of these numbers, right? Cosine and sine. And then the absolute value squared, this phase factor just disappears. And so, if you measure in the 0 and 1 basis, you can only get information about theta. Right? And so what we're going to have to do actually is we're going to have to measure this qubit, say in the 0, 1 basis, but we're also going to have to measure it in some other basis to figure out what this other parameter phi is in this case. So by basically doing like two measurements, working out two sets of probabilities, then we can work out what these two parameters in this case are, and that will tell us like what this state is. But what I mean here is that actually this needs to be done lots and lots of times, right? So even if for just like the 0 and 1 basis measurement, remember, we're dealing with probabilities here, right? So if we're dealing with probabilities, then we basically have to do some like statistics to figure out what the probabilities are. And then from the probabilities, we can infer what these coefficients are. So basically, this thing definitely has to be done like a lot of times in order to figure out what the actual state is. So even just for the 0 and 1 basis, you might do it, have to do it 100 times. So Alice is going to be sending like, say, 100 copies of this thing. Same state, 100 copies. He's going to do measurements, do statistics on it, figuring out the probabilities, from that work out this, and then actually do like 2 bases in order to work out all the parameters. So it's actually a pretty arduous kind of task to figuring out what a quantum state is. And so that's basically this process of quantum tomography. So, so what I'm saying here, So even if you guess the basis correctly and got the measurement outcome, with only one measurement outcome, he could not estimate probability, sample size is too small. So basically, this is basically what I mean. So you need to repeat the measurement a lot of times. And then finally, he would get the statistics. So, so what's going to happen is that Alice is going to send the same state lots and lots of times, and then Bob's going to receive it and figure out what the state is. So this is just actually my kind of cooked up procedure for doing tomography. Probably in general there's more sophisticated ways, but I think just schematically this is like the easiest way to kind of figuring to demonstrate how you actually work out what an unknown state is. So one way to figuring out an unknown state would be something like this. So Bob sets his measuring device to the 0-1 basis. Okay? And then he will repeat the measurement lots and lots of times, and then estimate these probabilities. And because in the 0-1 basis, it's just the amplitude squared, modulo squared of these numbers. So the probabilities that he'll get is cosine squared theta over 2 and sine squared theta over 2. And so to work out what the angle is, for example, one simple way is just to say, take the difference between these numbers, then it's cosine of theta, and then just take arcsine, and then you've got the angle. So now you've got theta, but we need phi. How do you get phi? Well, you have to go to a different measurement basis and work out what the probabilities are first. So for example, we can do it like the first way that I introduced. So given an unknown state in the plus minus basis, it's going to be these coefficients. So we did that before, and so in terms of our parameterization that we have now, then what we'll have in the plus minus basis, this state will be written as something like this. So it's basically this term divided by square root of 2, this term minus this term over square root of 2. That term. Then the probabilities of the two outcomes are just this modulus squared. Okay? So just take the modulus squared of this and a bit of algebra. Okay. So this thing is a probability, so it should be a real number, right? And so, for example, this term will give like 1, right? So that gives out half there. And this term will have a cosine of phi out front. And this term is obviously looking something like sine of double angle formula. So this term will give the second term, cosine phi sine phi. P of the other probability outcome is this term modulus squared. And this just looks pretty similar, except it has a bunch of minus signs. And so basically these two terms look pretty similar, except that this term has a minus, this term has a plus. And what we're trying to do here is to work out what phi is. So if we subtract these two again, then we'll get the second term, cosine phi sine theta. And from step 1, we worked out what theta was already, right? So we know what theta is from step 1. And then we just do arc sine of this thing. And then that will give us phi.
Previously, like if you know the cosine theta, like theta can be like minus or positive.
Right. Yeah. That might be a flaw in my procedure. Let me think. So you're saying you might have. Might be still ambiguous up to a plus or minus on the second term, saying B. Data. I think that so in the usual parameterization of this state here, theta actually only goes from 0 to pi, and if theta actually is taken to be negative, then that phase actually sort of appears here, and then generally I think that can be again absorbed into phi. So I think that eventually it probably will give the same kind of answer, because if you for example took the negative value of theta, then say in the first part, right, and And then this one will be negative. And then essentially then that would flip the sign up here. I think it might actually work out. I can't quite see it, but generally the convention is that, well, it's not really a convention, like the full parameterized, like the full set of parameterized states of this one, theta goes from 0 to pi, and then phi goes from 0 to 2 pi. So somehow I think that the negative values of theta actually kind of double count, or it's like, two values of the angle give basically physically the same state. So I think like the negative value of theta and possibly phi out by a factor of pi actually eventually give exactly the same state. So you don't need to count that because it will be kind of double counting the state. So I think it's fine, but maybe you can check this. Yeah. Okay. All right. Okay, but anyway, the main point I want to get here is not so much of this particular procedure, but the nature of kind of quantum measurements and how firstly you need to do multiple measurements in order to know what a quantum state is. It's actually a pretty non-trivial thing to be able to read out a state, unlike in classical physics where if it's 0, you just read it. Bang, you just read it out. 0, 0, 0, it's 1, it's 1. Quantum mechanics, you got to do this whole multiple measurements thing. So you might be doing this measurement actually thousands of times, even just to get like one parameter. And then you have to do it in at least 2 different bases in order to extract all the information. This is only for a qubit. So for a higher dimensional quantum system, actually there's more parameters, and more parameters mean more measurements that you need to be able to do. So the reason, okay, and I didn't even talk about the difference between mixed states and pure states, which I think we'll talk about a little bit more later. But so in the case of pure states, we only have to do 2 measurements. But if it's a mixed state, then what that means is that, for example, let's say some of the qubits that Alice sends has some noise, and so they were supposed to be the same state, but they're not exactly the same state. So that, like, these ones are all the state that it's supposed to be, but maybe some of these ones are like something's happened to them, right? States changed. Okay, in this situation, actually you need to do, you actually even need to do more measurements in order to figure out what the nature of the state is, because now not only do you have like kind of this the 2 parameters, theta and phi, but you've got sort of an extra degree of freedom because perhaps this state is something else, something completely else. So in this case, actually, in general, you need to do 3 measurements. And why is this called quantum tomography? It's basically because you guys have seen one of these machines, right? MRI machines. You know how it works? Like, you know what it does, right? Like, you get these pictures of your body and it's like 3D and like, it's like very detailed. So basically, this MRI machine is like a 3D version of an X-ray, right? So an X-ray, you just have X-rays pointing at you, and you just get like a picture. It's just 2D, right? Sorry, this is not MRI. Maybe this is a CT scan. The CT scan is sort of like an X-ray, but then you've got like X-rays coming in from all different directions, right? And so by looking at it from all different directions, and then feeding that into a computer, the computer can make like a 3D model of your body. So quantum tomography is a bit similar in that way that basically like one measurement is not really enough to get all the information. It's sort of like you only get like a 2D projection or something like that in the case of X-rays versus CT scans. By doing lots and lots of measurements from like different angles, you finally build up like the full picture of basically what the actual state is. So this is why it's called quantum tomography. Okay, I think we don't have time for that, so maybe recap on Thursday and leave it there. Okay.